So we talked about drift and diffusion current and how they're related. Now the really interesting thing starts to come out. Maybe you don't think so, but of what happens if we put a chunk of p-type semiconductor in contact with a chunk of n-type semiconductor. So in a p-type semiconductor, we'll have many more holes than we have electrons. And I'm trying to make them evenly distributed here, but I'm not very good at it. And I'm not very good at selecting with this iPad. And on the other side, we're going to have a bunch of electrons. And we could have more electrons than holes, or we could have more holes than electrons. So there's no reason for the concentration in the n-type region to be the same as the p-type region. We just have electrons in one area, what we call n-type, and we've got holes in the other area that we call p-type. Now, the majority is holes here. And over here we have majority carrier is electrons. But we'll have some minority charges. Let me write that in a different color. We'll have minority on the n-type side, minority carriers of holes. So we'll just put one hole in here randomly, and we'll put an electron in here randomly. So there are some electrons in the p-type side, and there are some holes in the n-type side. There just isn't very many. There's very, very few, but there are some. Now this location here, where they come together, we call that the junction. Sometimes they call it the metallurgical junction. That means the material junction. And if we zoom in on that junction, what we've got is a whole bunch of holes on this side and a whole bunch of electrons on the other side, and they're all free to move around, and they are moving around. They've got a velocity due to just the heat in the room and whatever heat they're at. So they've got some thermal velocity. They're all moving around, and it happens that sometimes an electron from over here is going to run into a hole from over there, and a hole is nothing but a missing electron. And so the electrons are going to tend to go, they're going to tend to move that way just by diffusion. The electrons are going to go that way. Why did I write holes there? And the holes are going to tend to go that way. That's just the direction they want to go. And whenever they meet, they're going to annihilate each other. They're going to be poof. So a hole is nothing but a missing electron. So if an electron from here joins up with a hole over here, the hole is a missing electron. We fill it with an electron from here, and they're both gone. They've disappeared. They're just poof. They don't exist anymore because the hole was a missing electron, and we found an electron. But there's a charge balance in this whole chunk of semiconductor, and we just happen to have some p-type area and some n-type area, but there has to be, this whole thing is neutral. It has to be. We have just as many electrons as there are protons in this whole chunk of material, and every hole is perfectly matched by a fixed negative charge. Every electron is perfectly matched by a fixed positive charge. So there's charge neutrality in this. So if we have electrons and holes recombining here, then that means that we're going to have to be bringing in some electrons and holes through outside terminals. And we can call these terminals, or this side, the anode. Anode. I'll write it up here. They're kind of antiquated terms, but they get used and the book uses them. So they meet together and they annihilate each other, and that means there's a charge imbalance. There'd be some fixed charges that are still left there, and that would call for more carriers to be brought in, and we'd have to bring in some current. If we've got holes moving into here and electrons moving into here, that would be the same as electrons coming out here, and those are moving in the opposite direction from the holes. I'll talk about that some more, but it works out. We've got current flowing there, and we'd have to have it current flowing there. Now, it's going to turn out that it's not going to take very long to build up or to annihilate all of these, because they're moving fast. They're moving really, really fast, these electrons and holes, just due to thermal energy. So by random luck, there's going to be a lot of electrons coming across here and randomly hitting or meeting up with holes on this other side and annihilating each other. And pretty soon, we're going to get a region built up where there's relatively few holes and few electrons. So I don't know why I drew this on the right side, and I'm not sure what color I want to switch to. But quickly, and we'll quickly end up with this situation where we've got lots of holes in the p-type region still. We're still zoomed in here. And we still have lots of electrons here in the n-type region, but we will end up with a region near the junction with a bunch of fixed charge. That's the dopant atoms, and they'll be left behind. The dopant atom for n-type area, when it loses its electron, it's got a positive charge. And for a hole, the dopant atom, when it loses its hole, or it's unfilled, leaves a negative charge. And we'll quickly have the situation built up where we've got negative and positive charges that can't move. They can't carry any current on opposite sides of the junction. And they'll build up, and so that we have a balance across them. So that means we have plus over here and minus over here, so we'll actually have a field. Yeah, that's a little too far. Oops. We'll have a field built up from positive to negative charge across this small little region. We call that small little region the depletion region because the free carriers have been depleted. The depletion region is this region on both sides that has all these fixed charges, and there's virtually no free carriers in this depletion region, just a whole bunch of fixed charges, negative and positive, and they're separated charges. And separated charge makes a voltage. It makes an electric field over that distance. And the electric field causes a current. And I should say also that the concentration of charges, we have a lot of holes here and a lot of electrons here, so holes want to flow this way, electrons want to flow that way, so that makes a diffusion current. Flowing from the holes going this way and electrons going this way. And then we have this high electric, or we have an electric field set up over this region. That's going to make a diffusion current that wants to flow. And so the E field causes a drift field, or a drift current. And what's really happening there? So we've got negative fixed charges. I'm not going to draw so many. Some of those look like pluses, but they're all minuses. And then we have plus charges on the other side. And I should have just as many on each side. And we've got electrons and holes. We've got this depletion region of fixed charges, which there's really very, very few free carriers in there. But there's a big field. And remember, there are a few minority carriers in both sides. Now, if these carriers have random motion, in fact, there's very few electrons in here, so electrons want to go from high concentration to low, so they'll flow into here. But if an electron gets in here, as it gets in here, it's going to see this huge electric field generated by all these fixed negative charges on the other side of the junction. And so any electron that wanders in here is going to get kicked out violently. So if an electron comes in, to here, it's going to get kicked out. But if a hole wanders in, as it gets into here, it's going to get sucked across to join up all these other holes. So what's happening there, if we talk about the majority carriers is they get into here, and these fixed charges are actually spread out quite a long ways, because remember, it's 1 in a billion charges are actually maybe not a billion, 1 in a million silicon atoms are actually a dopant atom, so there's 1 in a million atoms are dopant atoms, and so there's a fairly good chance that an electron can get into here. But when it gets into here, it's going to see this huge negative charge on the other side of the junction, and that's going to push it away. There's a strong field to push the electron away. But a minority carrier, which is a hole on the n-type side, if it wanders in there, it can also wander in there. And when it wanders in there, if it just happens to wander in there for a little bit, once it gets a little ways, it's going to see this huge negative charge on the other side, and that's going to suck it across. And as it goes across, it'll change from being a minority carrier to a majority carrier. So once the hole makes it past this junction, it's now a majority carrier, and it's sucked on through. Just the same way the majority carriers were kicked out here, the electrons, once it's in here, it'll be kicked out and accelerated across. And likewise, if an electron on this side wanders in, it's going to get sucked through real quickly. Once it gets closer to that junction, it's going to get pulled through, and this minority carrier electron will become a majority carrier in the n-type side. and a hole will get kicked out by the same method. If a hole wanders in here, it's going to get kicked out by that electric field on the other side. So majority carriers are kicked out of the depletion region, and minority carriers are sucked through and become majority carriers on the other side. And it's a strong, strong force causing that to happen, sucking them, pulling them through. And that will make some drift current due to minority carriers. So we have holes moving from here to, so holes moving from here to here, electrons moving to here to here. That means we have a drift current moving this direction. Across that junction. But as I said, these electrons are really pulled in through here, and these holes are really pulled in through here because there's these big concentration gradients, and that's going to make a diffusion current. It's equal and opposite. Very quickly, it's going to, at least. And eventually, very, very quickly, those drift and diffusion currents will balance out and set up equilibrium, and there really won't be any current flowing through there at all. Now, this field across this depletion region, it has a which is volts per distance. And that field is actually coming, or it's due to a voltage, or we can measure that field as a voltage, and we call that the built-in voltage. If we had a little voltmeter and measured from here over to here, we'd see a voltage. That would be V0, or the built-in voltage. And it depends on doping and how it's built and things like that. But that built-in voltage will be kT over Q, natural log of Na times Nd over Ni squared. That is, Na is the p-type, and Nd is the inside, and Ni squared is 1.5 e to the 10 squared. Those are the two doping densities, and kT over Q is 26 millivolts. .8 millivolts. That's what kT over Q is. So we have a voltage, 25.8 millivolts times natural log of Na times Nd over Ni squared. That's that voltage that's in there. So it's 0.0258 natural log of Na times Nd over Ni squared at 300 degrees K. This built-in voltage represents a barrier to charge movement. It's what's going to cause majority carriers to get kicked out and minority carriers to get sucked in, and that width of that depletion region. So there's a width here. There's a width W, and that width is dependent on the built-in voltage, which is dependent on the concentrations on the N and P sides. Overall, this device, we call this a diode, will maintain electrical neutrality if there's no electrical connections. It'll just sit there, and the diffusion and drift currents will equal each other. And so if we had, say, 10,000 fixed negative charges on the p-type side, and then there must be 10,000 fixed positive charges on the n-type side. But if the doping density is higher on one side than the other, it means it wouldn't take very much distance to make or to account for enough carriers for that depletion region. So I'll try to draw that. If we have if NA is much greater well, if NA is equal to P, and that's much greater than N, which is equal to ND on this side. This is the N-type. This is the P-type. So we might have the case where we've got a relatively low electron concentration, and we've got quite a high hole concentration. So we got lots of dopant atoms per cubic centimeter on the p-type side, but quite a low concentration on the n-type side. Then we will have a wider depletion region. Most of the depletion region will be in the n-type side, because if we have, so I've got 2, 4, 6, 8 fixed charges in the n-type side, then I just need 8 of these on the p-type side. 1, 2, 3. Let me get rid of a couple. We have the same number of fixed charges here as over here, but because of the higher doping, it takes a much smaller distance, a linear distance through this junction than it does in the n-type side. And so then we have W, and that depletion width is equal to there's an XP and an XN. And the total W is equal to XP plus XN. The total depletion width is equal to the depletion width in the N region and the depletion region in the P region. And there's an equation for it, 2 times epsilon s over Q times 1 over NA plus 1 over ND times the built-in voltage. And so that's in centimeters or something like that. And what we're saying is the total charges are equal. Total fixed charges So if the total fixed charges are equal, then we're saying Q times A times XP times NA. That has to equal what's on the other side, which is Q times A times XN times ND. And we've got QA and QA on both sides, so that those cancel off. And we're left with a relationship that looks like XP over XN is equal to ND over NA, that ratio of those charges. And the total charges is equal to A times Q times NA times ND over NA plus ND times W. That gets you total charges.